Welcome to Section 2 of Lecture 4. In Section 1, we described many elements of a closed-loop process. For this section, we will use a simple problem, a fluid heater, to illustrate differential equations and mathematics needed to describe the dynamic process and some elements in a closed-loop controller. We will not use this analytical method in class. The main reason to use this example is the mathematical approach to illustrate how complex even a simple problem is, which suggests that another method using Laplace transform is a better alternative for handling this problem and more complex problems. Next week, we will compare analytics results from today and with results obtained using Laplace transform method. You will find the results are the same using both methods, while Laplace transforms lead to much simpler calculations. The example is described in Chapter 4-3 of the course packet. This is a simple fluid heater. Here we use water as a specific fluid, so this is a water heater problem. The assumption for this problem is a well-insulated tank and well-mixed fluid. The purpose of insulation is to prevent the impact of ambient room temperature that will cause heat loss from the tank. We will use electricity to heat the water, and this simplifies the problem. This equation describes the change of the fluid temperature with respect to time t when heat is added. The details of the parameter are given in course packet Chapter 4-3. The left side of the equation is to describe the temperature change with respect to time t. Rho is the fluid density, V is the tank volume, Cp is the specific heat, and dTh over dt is the temperature change regarding time. On the right-hand side of the equation, we have Q as the heat input going into the fluid heater, which is the controlled input. The second term includes rho, the fluid density, V dot, which is the flow rate of the fluid heater, Cp is specific heat, and Ti is the inlet fluid temperature, and Th is the outlet fluid temperature at time t. The reasons we will clear later. We need to define several steady-state terms. These are variables that define the process when the process is at steady-state condition. These steady-state conditions are normal conditions and the error is zero, which is the outlet fluid temperature is equal to the set point temperature. Outlet fluid temperature Th will not change over time, so dTh over dt equals 0 in the steady state. Therefore, by moving Q to the left of the equation, the steady-state heat input Qs equals to the product of rho, the fluid density, Vs dot, the steady-state flow rate, Cp, the specific heat, and Ths minus Tis, where Tis is the steady-state inlet fluid temperature, and Ths is the steady-state outlet fluid temperature. This is how we calculate the steady-state input required. The user-specified tank outlet temperature is Tr. Ideally, error is 0, which means Tr equals Th. If they are not equal to each other, error will not be 0. The controller will adjust the heat input Q to reduce the difference between Tr and Th, which is the error. Later in the semester, we will consider to put the sensed output using a temperature sensor and the required input into consistent terms. Sensor output is voltage, and the feedback element will convert that voltage into temperature in the unit of degrees. We won't worry about this today. Go back to the fluid heater and corresponding differential equation. We need to decide which process input will change. The problem can be solved by handling one or more input changes. We will do that later in the semester. Today, we will handle only one input change to make the problem simpler. The three possible input changes are cold fluid inlet temperature, Ti, and fluid flow rate, V dot, and set point temperature, Tr. So the first two problems, we call them regulator problems, and the third, we call it a servo problem. And today we only talk about the first case, which is the cold fluid inlet temperature, Ti. How will the inlet temperature change? In process control, there are several common standard input functions used in analyzed process control systems. Step change is sudden upward or downward change in input. The plot is showing a downward step change. Another standard input function is a ramp change, where input linearly increase or decrease. The slope can be negative or positive, and it can be steep or shallow. Cyclical signal is another type of common input function, such as sinusoidal wave function. And impulse is also in the list. The best example of impulse for the water heater problem is to open the heater at the top and dump in some ice. The ice represents a sudden impulse of cold into the heater. The input functions can be combined too. Input functions are also called forcing functions. Again, we will go over all of these again in later lectures. Today we will use step change input for the fluid heater problem. Inlet temperature Ti is TIS at time t less than 0. It is common to assume that any change happens at time t0 or later. So at any time before t equals 0, the tank fluid temperature is TIS, which is the steady state temperature. At t equals 0, the inlet fluid temperature change by a step change delta Ti. In this problem, the inlet temperature stays at the new fluid temperature, which is TIS plus delta Ti. For this example, we set delta Ti to be 5 degrees Celsius. For closed-loop process control, we measure the outlet fluid temperature Th. Then we use Th to adjust Q by comparing Th with Tr, which is set point temperature. Our goal is to maintain Tr equals Th. There are other approaches rather than waiting to sense the output. Why not measure the internal process variable or all of the important process input before going into the process using a model or equation to adjust Q? Well, the advantage of adding cascade or feed-forward control is that they respond and adjust the process sooner. They got jump on process control. Cascade and feedback control are the best for a slow process with large time constants or where there is a lag in the process. Cascade and feed-forward control are usually used combined with feedback control, and we will talk about them later in the semester. Let's revisit and discuss more details about the process control Azure E, which is the difference between Tr and Th. Negative E means that the measured temperature is greater than the set point temperature, and we need to reduce heat. And positive E means that measured temperature is lower than the set point temperature, and we need to increase heat input. When we use proportional control, the control mode adjusts the controlled input in proportion to the error, as described in this equation. The proportional constant is Kp, which is a positive number. If the error is small, the adjustment is small. If the error is large, the adjustment is large too. So the equation is the heat input Q equals the steady state Qs, which is also the initial heat input, plus Kp times Azure, which is Tr minus Th. Now we substitute the Q in the original equation with Qs plus Kp times Tr minus Th. We will also simplify the equation by defining T equals Th. And we get the following ordinary differential equation that we are able to solve. We will divide both sides by rho times V dot times Cp, and then reorganize the equation to be the following. And we replace rho times V times Cp over rho times V dot times Cp with the time constant tau. And we're going to talk about time constant now. Time constant is an important term in dynamic process control and instrumentation analysis. The time constant has the unit of time, and in this example, it is in seconds. For the fluid heating problem, the time constant physically describes time for the entire tank fluid V to be replaced at flow rate V dot. Here you can see the time constant tau has the unit of cubic meter over cubic meter per second, which is in second. We will not go over the solution in detail as this is not the approach we solve the problem. The steps are listed here and you can find more details in the course packet. Here is the final solution for the fluid heater model, which describes the fluid heater response T to step change delta Ti in the inlet fluid, with proportional control. With these given values for calculating temperature change over time, we can get the graph. For fluid heater responses with proportional control of Q, the three curves indicate the temperature response with different proportional control constant Kp. The top line is the response from Kp equals 0, which means no control at all is applied to the water heater. The same heat input Q is applied to the heater. In this condition, the outlet temperature T will become 45 degrees C. The middle curve shows the response when Kp equals 414. And the long-term outlet fluid temperature is 43.7 degrees C. Later, we will learn that the shape of this curve and the amount of time the response reach plateau depends on the process time constant and the effects of any delays or other time-related elements. The bottom curve is the response curve when Kp equals 2070, which is a pretty big number. And the plateau temperature for outlet fluid is 41.8 degrees C. It is case-specific what parameter to choose. Are you satisfied with long-term outflow temperature to be 45 degrees C? It is 5 degrees higher than the set point. Then, can we get back to 40 degrees C, which is the set point? Not with proportional control alone. This graph shows one of the weaknesses of proportional control, which is an offset caused by constant changes in the input factor. This ends the example process control problem solved by solving the differential equation. We won't use this method because real-world processes quickly get beyond what we can solve analytically. To describe a complete control system, we need to consider additional model elements such as the sensor and feedback, actuators, as well as other control modes. In our next lecture, we will talk about using Laplace transform to get the solution. If you have any questions, please write them down and we can discuss during the class time. Thank you.